questions? The homework, I gave you the answers and solutions, I think, but I'm going to do a couple anyway. If you have questions, anyone bother you? Now, there's some with complex poles, and we don't do that. We use complete the square method, so you will not get a cosine of omega t plus 45 degrees as an answer. You're going to get a sine and a cosine. All right, they're separate. They are effectively the same thing as a cosine or a sine with an offset angle. But that's the way it's always done. Do you have questions about any of the homework at all? Please keep up with that. Don't get behind, because today we're taking off into the next stage. Any at all? None. Well, I'm going to do a few, because I want to make sure everybody understands these. And I know you've had partial fractions, but there's usually a few things you are familiar with, usually. First, I gave you
Can I give you one?
Yeah, go ahead.
Okay. It's 3.1C.
3.1?
Or 3.13, sorry.
13, okay.
3.13C.
Oh. All right. Read this one. This is the one with 3 of these poles. Okay, go ahead. Give me the top part first. Hold on. Is there a wastebasket around? No? All right. Give me the numerator of that.
Alright. 3S cubed
3s cubed
plus 36S squared plus 131S
Okay.
plus 144.
All right. Well, that's 12. All right. Then downstairs?
S times parentheses S plus 4 and then S squared plus 6S plus 9.
All right. Now, I'm going to tell you, the minute I see this, what I see at the base, when I look at this thing, I see 3 poles, here, here, and here. But this is a perfect square. So immediately I'll just put S plus 3 squared to replace that. Immediately. I'm going to do it right here. So this becomes S plus 3 squared. Now I look up here, I'm just telling you the way I look at these things. When I look up here, 144, that's 12 squared. 131, isn't that 11 squared? Or is it? No. I'm looking for things that give me 36 is 6 squared, things like that. I'm trying to find things that look like the perfect squares or squares, and that way I probably can manipulate this a little easier. I can't say that for sure. Now, when I do this, I'm going to have to find basically 4 coefficients. I need the 1 over S, so I have A over S, that's the first one, plus B over S plus 4, right? That's the second one, plus C over S plus 3, plus D over S plus 3 squared. Do you all understand why I've done that? Now, knowing that, I know each one of these when it goes back. I know 1 over S, if I have that, goes to U of t, correct, class? I know this one goes to e to the minus 4t, and the coefficient b, of course. This one is e to the minus 3t, and this one is what? T e to the minus 3t u of t, correct, class? So I know once I get these coefficients, it's game over, correct, class? And it's very obvious. But, I mean, you have to know which with the relationship between these poles in the S domain and the time domain form the caused it, understand? And that's something you get by just doing all the homework that I've given you. It should be very obvious by now, but it may not be. To get A, well, how do we get A, class? What's the bottom line? Anybody? Well, what I'm going to do is cover up the S, right? Cover up the pole and evaluate the remainder at the pole. The pole is 0, correct, class? Well, if it's 0, all these terms go away except the 144. Is that correct? So then downstairs I have 4 times 3 squared, or 4 times 9, right? Correct, class? Or 36, don't I? So I have 144 over 36, which is what? That's really, what? 4. So A is 4. This is all, I mean, this is how you do these, right? What's B? Just by looking at it. Cover up the S plus 4, right? This is a bit long, but you see I'm not doing anything tricky, right, class? This is very obvious how to do this. There's nothing tricky at all. I cover that up and I evaluate what's left at S equals minus 4. Can somebody do that for me? Because I'm not in the mood to do it. Wow, look, this is going to be what? That's 16 times 4 is 48 times 3. I mean, you can see how this is going to just be a lot of what? Simple arithmetic, isn't it, class? What's the number for B? For B, anyway. Please tell me. Do the math. I don't want to have to do all this. Come on, this is simple arithmetic.
I'm
Huh?
gonna say it's for 0 less than 1,000.
I can't hear you. What? I couldn't hear you. Did you say
He
B?
wants to just put it between 0 and 1,000. Just.
Do you know-
sure.
isn't it
negative one?
Negative 1, yes, thank you. Negative 1. All right, what's C? Multiply, cover up the S plus 3, put S equals minus 3. What do you get?
2.
You get 2? Good. Oh, no, I'm sorry. Sorry, you got to put S plus 3 squared, my bad, and then cover it up and evaluate S equals minus 3,
Yeah,
correct,
D
class?
is-
Then we can get this one. What is D?
That one's 2.
What is that?
2.
2.
That's what I meant.
Now for this one here, which was C, I have to multiply by S plus 3 squared, this whole thing, and then I have to take a derivative with respect to S, correct? Isn't that right? And then the remainder, after I take the derivative, I evaluate that at S equals minus 3, correct? And I mean, do you really want me to do that derivative? Because it's what? I got to take a derivative of the top times the bottom plus derivative of the bottom times, plus the top times the derivative of the bottom. If you want me to, I will, but it's a little long. What's that for part C? It's not hard to do, it's just time consuming. What is it?
C would equal 0.
Outstanding. All right. I mean, if you really want me to do the arithmetic, see me after class. It's just time consuming, more so than anything. It's not tough to do. There's no trick. Once we do that, now just take it back to the time domain. This one goes as 4 times class. Come on. U of T. Work with me. If you say it, you'll remember it. Remember that. That's an old lesson in the military. They really learn about how to make people retain. When you're asked a question, repeat the answer out loud. It's likely to stay with you. If you want a trick, some of you probably know this. If you read something and there's an answer, if you say it, you're more likely to recall. I don't know if you know this, but it's really true. So this one becomes what? Minus e to the minus 4t u of t. Make sure you put the u of t. Last one is plus 2 times, say it.
T
Right.
to the negative 3t u of t.
All right, and that's it. That's it. They're not meant to be hard. They're just, that one was a pain. Now, I do want to do a couple of them that I didn't have a chance to do last time. I want to actually, I may actually modify some of these. .316 part C. Could you tell me, I want to put that one right here and I want to work this. But I want to show you, they have complex poles for this one. I don't ever do complex poles. All right, can you give me, that's part C of 316, I think? I think it is part C. Yeah, it's minus 2 times, go ahead, tell me, minus 2 times what?
S squared plus 20
Over,
S times S squared plus 8S plus 20.
plus what?
20.
All right, now, when I look at this one, I want you to take note about this. Here, I have a pole of 1 over S, right? Give me that one, guys. And then I have another pole here, right? Now, what is this? That's quantity S plus 4 squared, right? Remember, take the middle term, coefficient of s, divide by 2, it's 4, right? So it's s plus 4 squared. I'm left with 16, right? But I got 20, so I have to add 4 right here. Don't I, class? Are you with me? That's what this is right here. How many see this? I'm completing the square. This is very important. Now, when I see that, I see an s plus 4 squared plus something. I think of 2 basic Laplace transform pairs. One is, I know e to the minus at, e to the minus at times cosine of omega naught t u of t goes to s plus a over s plus a squared plus omega naught squared. And I know e to the minus at sine omega naught t u of t goes to omega naught over s plus a squared plus omega naught squared. Does everybody see these relationships? These become critical. Understand? Now, when I come over here, I know I'm going to have some quantity bs plus c, because the order of the denominator in this pole is going to be s squared. Follow me, class? Please watch this. So now I put down s plus 4 squared plus 4. And now I start fitting forms on the second part. But first I'm going to get the coefficient of a very quickly. I'll show you this. Please work with me on this. How do I get the coefficient a? Class, just tell me what to do. And evaluate? All right, and what would that be? It's going to be minus 2 times 20 divided by 20, right? Or minus 2. Do you all agree with me, class? By inspection. So this is minus 2. Now this is an interesting one. Are you with me? When I do this, I know there's a pole here, but it's complex. It has a real and imaginary part. Follow me? It's not strictly real. So we don't bother with that. What we're going to do is multiply this side by s plus 4 squared times 4. Get rid of this, both sides. Follow me? And then we're going to evaluate the remainder of that at a complex pole. We could do it that way. Do you agree with me, class? You could do it that way. Or what you can do is equate coefficients. And it's easier to equate coefficients on this one. Do you all see this, class? So let me go ahead and do that. This becomes minus 2 times the quantity, and here it would be s squared plus 8s plus 20 plus, and then it's going to be bs plus c times s all over s times quantity, and I can just put this down here, s squared plus 8s plus 20. That doesn't matter. Now, what we do here to get the b and the b here and the c, we're going to equate the coefficients of the powers of s on both sides of this. Do you follow me, everyone? How many see what I'm doing here? When I say equate the coefficients, when I take a look at the coefficient of s squared on this one, what is it really? I'll put it over here. You can forget the denominator. Well, I have minus 2, right? Right? And then I have plus b. S squared. Because s is times this. Do you all agree with me, class? Keep going on. And by the way, now when I look at this, just by inspection of this one, we've got this. I know over there the coefficient of s squared is minus 2, isn't it, class? So therefore, what is b? It's 0, which is nice. I can get rid of this right there. So I just have cs here, right? Do you agree with me, class? Now we take a look at the coefficient of s plus, here I have coefficient of s is minus 2 times 8, or minus 16, correct? Plus c. And I see that that has to be equal to what? This is the coefficient of s, right?
Oh, 0.
0, correct, class? Isn't that right? How many see this right here? Can you see it in the back? I always worry about the guys in the back. All right, good. So I know that c also C is 0, right? And wait a second, I'm sorry about that.
B is 0.
Sorry, C is 16, my bad. C is 16. And I can put that in. So I have B was 0, correct, class? And C is 16. All right? I don't mean to move too fast, sorry. Agreed, everyone? Give me a show of hands if you see what I'm up to. Now, I put these back here. I'm going to go right here and do this. So I know B was 0, right? And now I know C in this one is what? 16, correct? You agree with me? Now look here, I'm going to put the 16 here. And I'm going to erase everything and talk about this so you can see exactly what I'm doing and why I'm doing it. Now, we've got the coefficients by simply equating the coefficients of the powers of s's, right? And we've got a common denominator. But we calculated one of them to make our life easy, correct? We calculated the first one, right, class? Just the 1 over s coefficient, right? Now when we do this, you know this goes back to just u of t times minus 2. What about this one? Oh, sorry. This is 16, right? Just 16, pardon me. Correct, class? Now when you take a look at this one, you see this is 4, but this is omega naught squared. Therefore, omega naught here is 2, correct? Here, that's A, and A is 4. Agreed, class? Now look at the form you want to meet. I want this form, omega naught over s plus a squared plus omega naught squared. Well, if omega naught is 2, I need a coefficient 2 here, correct? So I divide 2 into 16 and I get 8, right? And now I have what? I have 8, right? Times 2 over s plus 4 squared plus 4, right? And now this that I'm going to circle is this form. Exactly, isn't it? And that 8 is just a coefficient. How many see this? Now I can take this whole thing and say when I go back this way to the time domain, this is minus 2 times u of t plus what?
8
Say it.
e to the minus 4.
Oh, well, you want to do it that way? All right. It's 8 times what? E to the minus 4t, go ahead, times? Cosine of? Sine, right. It would be cosine of 2t plus 90 if it was a cosine. It's the sine, right, of 2t u of t. What does the answer in the book say? I have no idea. If they did it with complex poles, they're not going to get that. They're going to get a cosine. What was the answer in the solutions manual for this?
They gave a solution for cosine and sine, right? They're both equal. So sine of 2t, and then it's also equal to cosine of 2t minus 90.
Yeah, but that's stupid. This is this is the answer. I'm sorry, serious. This is the x of t. Follow me on this, class? If that's x of s. Got it? Now remember what I just did there. If for whatever reason you solve for a b, you had bs plus c, then what you would have to carefully do is factor out the s plus a. You find a, you factor out s plus a times the coefficient, and plus another coefficient times your omega naught, because then you're going to have the omega naughts over s plus a squared plus omega naught squared, and you'll get a cosine with an exponential and e to the minus at and a sine times e to the minus at that are additive. And there will be no angular, you won't have cosine of omega t plus 45 degrees or something like that. You'll never get that, but you will get a cosine and a sine together. Are we clear on that, class? How many understand this? Just be aware, always equate coefficients, then fit forms, and you must know these forms. You've got to know these. All right, have to. Other questions about the homework? I figure I'd get the last one, 21. Nothing? You got that one?
I just have a comment about that document.
What? Couldn't hear.
I have a comment about this way.
Yeah, go ahead.
So if you find the roots of the denominator and then substitute the roots and express the answer in the...
But the roots are complex for this one. You have conjugate pairs.
Yes.
So then you would have to bring out a you would have a over s minus the first pole, which
Yes,
would be
then
real,
you're
and then
gonna-
plus A conjugate over the second pole.
Yes. Then you're gonna express it in the polar coordinates. Wouldn't that be more straightforward than the way that
You don't have a calculator to calculate the angle. You can't get that with a pen and paper for anything but a simple thing. All right? That's the reason you always go sine and cosine. And by the way, I want to tell you one other
Yes,
thing.
but you can convert and write z is equal to r plus ra.
You know, listen, I guess what I'm saying is, when you're talking about, you have e to the j, like pi over 9 as a coefficient, and then an e to the minus j pi over 9, and you're trying to get a real and imaginary, you know, you have to expand that in terms of real and imaginary part. You can't do that without a calculator. Right? So it doesn't serve the purposes of this course to do that. This is the more straightforward way. To be frank about it, it's the better way, honestly. All right. Anything else before? I mean, you know, the last problem was a circuits problem, wasn't it? All right. I figured I'd get a question. But maybe you guys are circuits whizzes, all right? We'll do it though. The reason I threw that in there, today we're going to be dealing with real circuits. And you're going to be introduced to operational amplifiers too. All right. Now the last problem. This is 321. Here I'm going to show you something. I'm going to go through a lot of them. Look at this. They have a simple circuit like this, plus and minus Vs of t. Then they have R1. They have a capacitor C. We have R2. And then they have L here. They want to know what this voltage is, plus the minus V of t here. And they give you some stuff. Vs of t is 2U of t. R1 is 1 ohm. R2 is equal to 3 ohms. And that capacitor is a crazy value. What is it, 0.369? Farads. And the inductor's value is 0.2259. Now I'm going to show you something. How many actually tried this problem? I didn't think anybody. I thought you'd try it, but you wouldn't know what to do with it. All right. The reason is this is something where the way you should have done it is write differential equations and some of the voltages around the loop. Now that's the normal way to do it. So what I'm about to show you is going to save you a lot of anguish. I'm going to show you something. Put this down. Put time domain or t, and then put S domain here. Now, in circuits, if you have a resistance R, in the S domain, that we call the Laplace domain, when you take a Laplace transform of the differential equation, it'll look like R. Right? It's just R. These are the impedances. In the time domain, you know, with a capacitor, you have C times dV dt is equal to I through a capacitor. Isn't that right? The capacitor times dV dt is equal to the current flowing in. So if I look at this and do the Laplace transform of this, on both sides I have I of S is equal to S times C times V of S, and this is assuming no initial conditions. By that, it means there's no voltage on the capacitor to start with, or I'd have to subtract that part off. But for now, ignore it. With me? No initial conditions. Understand? There's no initial conditions on that one, is there? There's no energy in the capacitor, t equals 0. Now, that means what? When I take a look at the ratio of V of S over I of S here, that's something 1 over SC, isn't it, class? And that is an impedance. That's like the impedance of the capacitor as a function of S. Now, do you remember in circuits, when you had a constant frequency that you found out that the impedance of the capacitor was 1 over j omega c. Y'all, how many remember that? Well, S is equal to sigma plus j omega c, or j omega, pardon me. And for this, when we're doing these problems, they are like circuits problems with sigma equal to 0. This is the way you think of them if there are no initial conditions. Understand, class? Remember that, no initial conditions. I'll get to the initial conditions next, but I want to show you this simply. And I chose this problem for a reason. So really the capacitor, if we just have a capacitor C, in the time domain, the impedance in the frequency domain would be 1 over SC. How many have seen this before, by the way? Did you have it in what course? What's that? In Erwin's course? Who'd you have for circuits? Did everyone show you this stuff? I mean, he used j omega though, didn't he? All right, because we used to teach Laplace transforms back in the day, but I don't think he does. I think he just used j omega, does he? All right. So this is the impedance of a capacitor. Now, if you have an inductor, remember for inductor, I'll do it here. It was what? L times di dt was equal to the voltage across the inductor, V of t. And I'm being a little sloppy with this because we're electrical engineers. You've had this. You know what an inductor looks like. If there's a current I of t here and there's a voltage V of t here, an inductance L, this is the differential equation that governs the relationship between current and voltage and inductor, correct? That's not exactly true. I'm going to do this just for you people. When you get down the road, actually if you have an inductor there, the voltage across an inductor is equal to d dt of the product of L times I. Now, if L varied with time, then you would get dl dt times I plus, and then it would be L times di dt. Do you follow me on this? The reason I say this is because oftentimes electrical engineers, especially, they just instinctively say this. And the reason that's not entirely true, and this happens a lot of times when you're dealing with high energy physics kind of things and specialty effects like EMP flares. If you take an inductor, say you have an inductor, in the center of that coil we have high explosive. What we're going to do is we're going to put a whole lot of current through that coil. Now, you know one thing about an inductor. If you try to break the current flow, you'll see an arc across a switch if it's a big inductor. How many know that? All right, it's continued because it doesn't want to change the current. It wants to keep that current going. There's almost a momentum to the current with a large inductor. Well, if they want a really large voltage so that no matter how far apart you spread the switch, it'll keep arcing, what they'll do, and I've been at Eglin Air Force Base when we've done these kind of things, they'll get a large inductor and they'll put a lot of current. Now remember, their goal here is to generate a ginormous voltage, something extreme. And what they'll do, as they theoretically throw the switch, really open the circuit, because they're going to put something on there, they want an enormous voltage, then they'll blow up the inductor simultaneously. In the process of the thing blowing up, the inductance is changing rapidly, and this term overwhelms the voltage, and it becomes ginormous. That's the term I use. It's enormous. They use these things. If you want, say you want 50 amps to generate a voltage of 12 million volts just for an instant in time for some kind of a impulse antenna, you can do it this way. Just remember that. So that's fundamental. Back to the reality for us, our inductors don't blow up and they don't change with time usually. If they do, you got a problem. So when we take a look at this here, V equals L di dt, and you know that that means V of S, right, is equal to S times L times I of S. Now impedance is always a ratio of voltage to current, so you can all see that the impedance of that is just SL. And back in the day, you remember the impedance of an inductor was just J omega L, right? Constant frequency, so think that way. So that means for an inductor, the impedance is simply S times L in the frequency domain, or in the S domain, okay? Now, back to this problem. I figure this problem, this at least should look very familiar to you in terms of things you've seen before with circuits, right? I'm going to leave that up here. So now I have an impedance here of R, and by the way, do the Laplace transform of any kind of time domain function when you do this kind of problem. There's no initial condition. What's the Laplace transform of 2u of t, people? Just 2 over s. So put it in there, 2 over s, right? There's R. Now, they want V of t. Really what they want is the voltage across that, but we're going to put the impedance there. The impedance is 1 over cs, right? For that, I'm not even going to bother with the values. So this impedance right here is 1 over cs. Don't even worry about the values. The impedance of this guy is s times L, correct? And the impedance of R up there is 3 ohms. Now, if I wanted the voltage across here in the Laplace domain, how would you get that? There's a couple of ways. How would you get it? You're electrical engineers. You just had David Irwin for circuits, most of you. He's the best circuits teacher in the country. How would you get that voltage? Think of this as like 10 instead of 2 over s. Well, you could do it a few ways, right? You could say what I'll do is I'll write a loop here and a loop here. Set the sum of the voltages around an enclosed loop equal to 0 and start 2 currents through it, right? You could do nodal analysis, correct? And the node voltage, that means you ground that. You could just say the node voltage here is the unknown voltage V of S, correct, class? I get it that way? That way looks pretty easy. What do you think? But we could do it a number of ways. You all see? There's not one way. You could do it with loops. You could do it with loops, mesh, right? Nodal or mesh. You could also do it by saying, well, these two are parallel. I can get a parallel impedance there, right? That parallel impedance is in series with this, and if I want this voltage, it would just be the parallel impedance, right, divided by R plus the parallel impedance times this. That again would give you the correct answer for the voltage across the capacitor. Do you all see this? There's not one way. There's a many ways usually. So if I was going to do this and I was going to do it with nodal, I'm solving for V of S, then I'm solving for a current here, I'll call it I1, a current here, I2, and a current here, I3, correct? Do you all agree with that? And so if I'm going to do this, now, I'm going to erase these things. And this is like electrical engineers' bread and butter doing this kind of stuff. You always ground one end of these things with nodal, if you remember that back in the day. So when I'm doing that, I'm going to say first that I1 equals I2 plus I3. Does everybody agree with that, based on what I've drawn? Keep going. What is I1 in terms of the voltages? Well, I1 is the voltage here, that would be the positive side, minus the voltage here, divided by R. And that's simply 2 over S, right? Minus V of S divided by 1. Do you agree with me? Because R1's 1. It equals what? I2. What is I2? Anyone? V of S, right? Divided by 1 over CS. So really it's V of S times C times S. Isn't it, class? If it's divided by 1 over CS, it's multiplied by CS. Isn't it, class? Keep going. Finally, what's the last? What's I3? Plus? Come on. Well, voltage what's the voltage at the node, people? V of S divided by
3 plus SL.
3 plus SL. Now we can put in the values for S and L in a second, but do you all see this, class? What's the next step usually? Well, we have to solve for V of S, correct? I don't care how you do this, but this is usually not too hard. I'm going to take that V of S to this side. So it becomes plus V of S. You all give me that? Now what am I going to do? I'm going to get the coefficient of V of S, right? I'm going to see what it is. So V of S here is on this side is equal to 2 over S. Keep going. What's the coefficient? It's going to be 1, right? 1 plus. And well, how about maybe I'll do it this way. I'll take the highest order one first. I'll take C of S, and I'll show you what I'm up to. Plus 1, right? Because coefficient of V of S is 1, correct? Plus what?
It's 1 over 3 plus SL.
Mm-hmm. Don't worry about what the values are. Are you with me so far? Now at this point, I also make the observation, there's a 1 over 3 plus SL that I don't want there. So I'm going to multiply both sides, this and that, by 3 plus SL. Understand, everyone? So I get 3 plus SL here. This one goes away, right? It's just 1. Right? And then I've got quantity 3 plus SL here as well, plus 1. I'm just simplifying this down. Do you see what I've done? I wager a guess that C times L has a very interesting product. I'd like to know what that value is, but it doesn't matter at this point. Now what I'm going to do is divide everything by this quantity right here. Got me? And so if I divide over here by this, I get C of S, or CS plus 1 times 3 plus SL plus 1. And lo and behold, now I have V of S. Does everybody see what I've done there, class? How many do right here? All I'm doing is what? Cleaning it up so I have all the unknowns on one side and V of S on the other. Now V of S is the voltage I'm after, correct? Now I take a look at this, and I'm going to multiply this stuff out. First I'm going to come down here, and I have 3 plus SL times 2, then it's over S, then it's this. Now I'm going to get the coefficient of S first, which is going to be L times C, or S squared, pardon me. So I have L times C times S squared. Then I take a look at the coefficient of just S, and I have 3 times C and 1 times L, so I have plus 3C plus L times S, and then I just plus 3 plus 1 is plus 4, and that's my V of S. Remember, I haven't put in the numbers for L and C yet. Follow me? How many see what I've done so far? I'm just what? Trying to condense it down to something's manageable so I can start seeing where the poles are. Now, whether you know it or not, in your brain you say, well, the highest power of S has to have a coefficient of 1 to make sense of these things, right? So I divide everything but by L plus C, top and bottom. Understand that, class? That's L times C. So if I divide top and bottom by LC, this goes away, right? And then I get this divided by LC, I'll clean it up in a second, and this divided by LC. And on top I put 1 over LC as well. Correct, class? How many see what I've done so far? And now I take a look at what's left. Now I have this term, 3C plus L over LC, and I have 4 over LC, right? So do me a favor now, just to help me out here. What is 1 over LC for this problem? I don't know how he did it, and I don't know what that is. Can somebody tell me what it is? Come on, you got calculators, right? No? Help me out. I'm doing you a big favor here. You have no earthly idea how much of a favor I'm doing you, because you don't know what's coming next. I'm trying to show you the simple way to do these problems. Anybody? Anybody at all?
It's 11.9.
11.99? 0.99? That's 12.
Okay.
So L times 1 over LC is 12. Good. That means what I can do here is take 1 over 12. I want to put 1 over 12 here. Right? And then, I'm sorry, this is 12 times this. Now, I'm going to tell you what really happens here. This is going to be a single number, and this is going to be a single number. Follow me? Now, can you see you can complete the square on this one very easy? I'm not sure where the poles are, if it's a double pole or if there's a complex pole here. But you all see if you have S squared plus anything times S, if I take that anything and divide it by 2, and I take S plus that anything divided by 2 squared, plus whatever the remainder is, you have to subtract that from this, which is what? 12 times 4 is 48. Subtract the remainder from that, then you get this term. And now you're fitting the form. You're fitting those forms that were up here, and you can get the answer to this very easily. In the book, what does he give V of S as, by the way, for that problem? That's problem 21. Can you got, I see these people.
2 U of T.
What?
2 U of T.
Just 2 U of T?
Yes. 2 times U.
So that means, if that's the case, 2 U of T, huh?
So the answer?
That's the answer for V of S?
Did you want the answer to the voltage source? The voltage source.
I want the answer for V of S, the voltage across here. I know that's 2 over.
Yeah.
Does he have it? V of S in terms of time domain? He should.
Yeah, it's 1.5 over S minus 1.
No. Give me the term in terms of T.
Oh,
Sorry.
1.5 minus 1.56 e to the negative 4t plus 0.072 e to the negative 12t u of t.
And there's no sine or cosine? All right, that means that this pole here is going to be 2 simple poles. All right, it's not going to be a double, it'll be factorable. All right, I didn't factor it, but this is the way you go about doing it. Follow me, class? The numbers are a little bothersome. I thought you have nice easy ones, but remember what I've just showed you. That's with no initial conditions. With initial conditions, you have to do something else. Yes, sir? Yeah.
So, if 1 over LC equals 12,
You tell me what this number is and we can solve it fairly quick. This number's 48. I can put that in. So that's plus 48. Tell me what this number is. 3C plus L. You're gonna have to tell me because it divided by LC is, or times 12. What did you get? What did you get?
1.33.
That's the coefficient of this, S? 1 point what? Say that again?
It'd be 15 or 16.
It's 16? S?
Yes.
Oh boy. Is that, and, well, if I'm looking at this,
how do we get that? I don't think that's the story.
I couldn't hear you say, who's talking? You didn't get that?
Why do you have the bottom 48 while the top one's?
I'll tell you what, we can, I don't want to waste more time on this one. What I wanted to do is show you that if you're solving for anything, you can solve this thing with your circuit, all the basic circuit analysis techniques. You can do it with loop, you can do it with, or mesh, whatever you want to call it. You can do it nodal, or you can do it just by doing voltage division, by getting parallel values of resistance. And the bottom line is you're going to get a V of S and everything on the other side, and then you're going to solve for that V of S. And then you do the method to get the time domain form, just like we've been doing, the inverse Laplace transforms. Understand? That's what you're going to be doing from here on out. This problem was to introduce you to that. Now, there's plenty more I can talk about here, but that was a pretty good beginning to it. And I wanted to introduce you because you've had the circuit analysis techniques. I want to do one other thing for you. Everything I'm showing you here, we've done repeated poles, we've done this other stuff. I'm just going to talk about one other item. And I want to do, hopefully I can do 2 things. All right, now, something I want to make sure you understand. When we talk about Laplace domain or S domain, there's a term that comes up called stability. And here's what it means in a nutshell. If you're in the S domain, this is the S domain. And this is going to be the real part of S, or just sigma graphed on this axis. This axis is going to be the imaginary part of S, or it's just j omega going up. Because remember, S is equal to the real part sigma plus j omega. This is called the complex plane, and this is 0, dead center there, all right? Now, anytime you have something that has a pole, for instance, if I had A over S, and they always put minus the pole P1, that pole, wherever it exists, right? In this case, it would be at S would be at, the pole would be P1. Do you follow me on this? I put a minus sign, most of the time it's plus. The way it really should be represented is plus, or I'm sorry, is going, yeah, plus a minus P1, if you think about it that way. Now, if that pole, if S has a value, and it's on this side of the complex plane, anywhere over here, anywhere at all, this is called the left-hand plane of the complex plane, then if the pole is in this side, it's stable. Oops, excuse me. If the pole is in the right half plane, it's unstable. And unstable means the solution will go to infinity. Something will blow up. Now, let's just take a look at this for a second so you get an appreciation for it. Suppose I had 2 over S plus 4. What's the time domain formula? Just tell me. 2 times e to the minus 4t u of t. Do you see how that's asymptotically approaching 0? It's not going to infinity. It's stable. It doesn't blow up. That's the term I like. The function's not going to plus or minus infinity. Let's, by the same token, see what 2 over S minus 4 goes to. Go ahead and say it. That pole's what? Plus, what? Say it. 2e to the 4t u of t. Where's that going? It's blowing up, right? Where are the poles located? This pole, S, would be minus 4. It's over here. It's at minus 4. By the way, poles are symbolized by x's. Where is the pole in the other one? Plus 4. And it's blowing up. Follow me? So when you do this is very important for stability analysis, and it comes in a little bit when we do this. When you get a system, you can do pole zero constellations. You can get real quick with MATLAB. You see any pole in the right half plane, after you do feedback and stuff with your system, you have a major problem. Your system isn't going to work well. And if it's designed to blow up, you've done a great job. But otherwise, you've got a problem. Remember what I'm telling you, people. Now, if we have a system and initially it has poles over here, we can do things called feedback and move the poles to the other side and make it stable. And this is where we're going with this stuff. I got to show you a couple more tricks with circuit analysis and things with operational amplifiers I didn't have time to today. And then you're going to get the big picture. And I'll tell you one thing you might like. I don't know if you will. How many people have heard of Bose speakers, B-O-S-E? I don't know if you know the history of it. I saw it used to be a high fidelity guy back in school. That was, a long time ago. Everybody wanted the best high fidelity systems. Well, Bose was a guy at MIT, and he did too when he graduated from MIT. Brilliant guy. He's a professor. Was a professor there. And so Bose realized even when he bought the best speakers, they still stunk. So what Bose did is said, being an electrical engineer, I can do one better. He got a bunch of cheap speakers. And what he did is he looked at the frequency, the power output versus frequency. And instead of going, you would like it flat, right? For any frequency, if you have a certain 1 watt of power, you'd like the same amount of volume, decibels coming out, right? That would be a flat response. And you'd like it clear. But what he got was, they do all sorts of things. So what Bose did is he took that frequency response and he did the inverted of that, and he created an amplifier which is exactly the opposite or inverse properties as the speaker's response. So when you fed the output from your actual amplifier into this filter, then you got something that would throw in power at all the different frequencies that would make the frequency have a flat response. Follow me on this, guys? So he basically allowed the filter to invert the bad performance of the speakers so you get flat output. He took cheap speakers, but he took an active crossover. It's called Bose 901. I remember these very well. And that sounded unreal. It was unreal. He used cheap speakers, but an active crossover to get unreal sound because he was in electrical engineering, marketed. I have Bose speakers in my house now. It's one of the most popular brands. Does anybody own Bose speakers for your car? That's Mr. Bose. You got to read about it. Dr. Bose. And that's what you can do. And the thing I remember the most when you were, I liked high fidelity sound. I liked flat sound, but I didn't have a lot of money. But I had big transformers available to me. That's where all the money is in amplifiers, because we had a place called the Dungeon where I was at, where they threw all the old equipment. You could tear anything you want out. So you get the biggest, hugest transformer, so you can get all the power you want out. And we built amplifiers, but we didn't make them flat to 20,000 hertz that had no intermodulation, distortion stuff. We had a guy named Jack Carlson, who was a genius at this stuff. We made them flat to 100,000 because we didn't care about over-design. The parts were free. Not only that, we made it 100 watts RMS per channel. And beyond that, and Carlson was this is recorded, isn't it? Before I get more lawsuits. I don't have that great of a legal team, so I'll just tell you, he designed speakers, but I didn't know this. Some of you probably do. When you make them out of concrete, they don't move very well, but they're the best speaker cases you can get because they don't vibrate at all. And you can use low efficiency. Anyway, what we did was, and you can do it too, you should do this with senior design, find something you really want to do. Your engineers, there's nobody that's going to tell you what you can't do. If you want to over-design on stereos or whatever, drones or whatever, now's the time to do it. Because you can do anything you want. You don't have any time constraints in a sense. You've got all the parts you want, dirt cheap, and you're engineers, so you can over-design everything. So I'm going to show you how to do some of these things, but this class benefits you in these areas. When I had kids do this stuff, by the way, I even had a kid build a super subwoofer.